Hello everyone, my name is Petar Ukmirovic and I will be talking about porting some techniques from SAT solving to superposition that are used for simplifying and eliminating clauses. So to begin, let's look at those theorem provers for propositional and first order logic from a bird's eye perspective. So if we take a very far away look, we can actually see that they work by first taking the input problem, passing it to some kind of preprocessor, and then giving the simplified problem to the prover. And the prover has the main calculus which actually generates clauses, and whenever it generates a clause, it asks a certain simplifier or in processor whether a clause can be eliminated or in some other way simplified. In the case of propositional logic, the calculus of choice is usually CTCL, and preprocessor and in-processor use more or less the same techniques, because in propositional logic and in CTCL you can eliminate the clause as long as its removal doesn't affect the unsatisfiability of a problem. What also was noticed in propositional logic was that preprocessor gave certain improvement, but where the real gain was in processing. And in processing, you gain even more. Now, in first order logic with equality, state-of-the-art calculus is superposition, but the in-processing engine, which simplifies clauses, actually can simplify a clause only if it adheres to certain redundancy criteria, which is more strict than what we had for propositional logic. However, preprocessor can, in principle, remove any clause as long as this doesn't affect unsatisfiability. So preprocessor and in-processor use actually different set of rules to simplify clauses. Moreover, the set of techniques that are used for preprocessing in first order logic is a little bit smaller than in propositional logic, because not all of them are directly applicable in first order logic. This is why we set two goals in front of ourselves. The first one is let's try to see how we can port as many techniques from SAT solving as we can, and the second one is let's see if we can port them not only as pre-processing techniques, but let's try and make make them work with redundancy criterion. So make them work as in-processing techniques. The first technique that I want to talk about are so-called hidden literals. So in propositional logic, it was noticed that whenever I have this binary clause, well, I can also read it as a binary implication of this kind. Furthermore, if I have multiple binary clauses, I can create transitive chains of those implications. And in this particular case, I can actually create a chain from not P to R. And then we say that not P is a hidden literal for R, or more generally, whenever I can create such a implication chain from P to Q, I say that P is a hidden literal for Q. Now, what can we do with those hidden literals? What we can do is whenever we have a literal and its hidden literal that occur in a clause together, we can actually remove the hidden literal, and this is called hidden literal elimination. Furthermore, if we have a literal and a negation of its hidden literal in a same clause, we can remove the whole clause, and this is called hidden tautology elimination. Hidden literals weren't ported to first order logic before, and to port into first order logic we needed to deal with some features of first order logic, such as substitutivity of variables and this interpreted equality, etc. But the main principle of I can read a binary clause as an implication still holds in first order logic. And then the first thing that we need to deal with is simply I can replace any variable by arbitrary expression, and this means that this implication does not hold only for these two literals, but also for all instances of them. But more interestingly and more importantly, because we assume first order logic with equality, we need to take care of properties of equality, and the most important property of equality is congruence. So whenever I have that a certain equality holds, I also have that this equality holds under any context. So whenever I build more function symbols around this equality, and this further means that using congruence of equality, I can create a chain from P of x to Q of x, even though the left-hand side for the first, even though the right-hand side for the first implication was not syntactically the same as the left-hand side of the second implication. And more generally, when we looked in propositional logic, we said, okay, we can just create a transition whenever we have a binary clause, but now this is more complicated in first order logic. So in first order logic, we can create a transition whenever we have a binary clause, but not for these two particular literals, but for any instance of these two literals. Also, whenever we have an implication, whenever we have an equality, we have that this equality holds under any context. Whenever we have a disequality, we can take out the particular elements under the same context, and then state that those elements that are under the same context must be different. Now, the definition of hidden literal still stays the same. If I can create these transition chain from one literal to the other one, the first one is a hidden literal, and it turns out that hidden literal elimination is a simplification that can be applied in first order logic, and it adheres to standard redundancy criterion. However, removal of hidden tautologies does not adhere to standard redundancy criterion, and if we apply it, if you just blindly remove hidden tautologies, this would influence reputational completeness of superposition. Now, what we can do is we can actually shorten every hidden tautology to the binary subclause, which makes it a hidden tautology. And also in the paper we describe more elimination techniques which make use of the fact that superposition provers keep unit clauses around, and we also port another technique which is related to hidden literals. They are called fail literals, but I won't go into details of these here. How is this implemented? Well, you could already see that in first order logic we just we have a bound on the length of chains. So because in first order logic chains can be chains can have infinite length. And how do we efficiently implement it? Well, what we do is we keep a mapping from a literal to all of the literals that it implies, and we to make those lookups efficient, what we do is we implement this mapping as perfect discrimination tree, and this is a data structure that makes those lookups of does a literal imply another one more efficient, and we make sure that we do a little bit of garbage cleaning in this data structure. So this means that, for example, if I already have in my data structure that P of X implies Q of X, then I will not insert that P of A implies Q of A, and vice versa. If in my data structure I have that P of A implies Q of A, and later on I derive that P of X implies Q of X, the one that is already in the data structure is going to be subsumed by the one that I insert. The second technique that I want to talk about is so-called variable elimination in propositional logic, and this is the idea that you can simplify your proof state in your SAT solver if you actually eliminate one of the variables. And how do you do that? Well, you choose a variable and then you split your proof state into clauses where the variable occurs positively and the clauses where the variable occurs negatively. And then you compute the resolvents between the two sets, and then so you compute the resolvents between any two of these clauses, and then you get this set which is of quadratic size. And if certain measure is satisfied, I won't go in details of this, then you can replace the parents with the resulting set. Now, obviously this set can be quite large, so we would like to compute less resolvents. And how do we do that? Well, what was noticed is that a lot of times there are subsets such that they define P to be logical gate. This means P is some logical operation over other propositional variables. And if this is the case, if such a subset exists, and in this case such a subset would look something like this, so those three clauses together actually say that P is a conjunction of Q and R. If this is the case, then we have to compute much less resolvents. In particular, we need to compute only resolvents between the gate and the positive, and the gate and the negative occurrences of this propositional variable P. And clearly this is much smaller set. So in first order logic, predicate elimination was previously generalized using something called flat resolvents. So flat resolvent doesn't compute the MGU, most general unifier, like a normal resolvent, but it simply decomposes the arguments. And there was one constraint, which is that you can only eliminate a predicate if a predicate is such that it occurs at most once per clause. And this was already done before. But coming back to our questions, so the first question that we ask ourselves is, can we lift this optimization, which is, can we somehow generalize the concept of gates to first order logic so that we have more optimized predicate elimination? And the answer is yes. So how do we do this? Well, we have this definition of a definition set, which is a generalization of gates, and together with it we have an efficient procedure to check if something is a definition set or a gate. And in first order logic, those definition sets look something like this. They're pretty flat, so under a predicate symbol we can only have variables, and what occurs in the rest of the clauses need to have variables that are a subset of what occurs under the symbol that we want to that is defined actually. So if P is defined here, then all the other literals need to have variables which are subset of the ones that are applied to P. And there are some other conditions in which I won't go into, but this is in general the look of the gate or the definition in first order logic, and the same as before holds. So we just need to compute a certain subset of resolutions, but there's something interesting here. So this singularity requirement that the predicate that we want to eliminate occurs only once is true only for the gate. So in the remaining clauses of the proof state, P can occur as many times as you want, and because here we have this flat shape of a gate, you don't have to compute the flat resolvent, but you can actually just compute a normal resolvent, and this would be the set with which you would replace the original clauses. Now, the second question that we ask ourselves is, can we use this as an in-processing rule? And the answer is yes, with a small asterisk. And this is if our calculus uses no splitting rules. Now, let's see. The last technique that I want to talk about is block clause elimination. And in propositional logic, we say that a clause is blocked if there is a literal such that whenever I resolve against this literal with other clauses, all the resolvents are tautologies. And block clauses can be removed without influencing satisfiability of the problem. And block clause elimination was already generalized to first order logic using so-called flat L resolvents. And now coming back to our two challenges, we looked at are there any other uses for block clause elimination, and block clauses were originally just generalized as preprocessor. Our question that we asked ourselves was, can we use block clauses as an in-processing? Can we use it together with superposition? And to answer the first question, let's look at this example. This is a simple two-clause example, which is clearly satisfiable. So we can take a model which is, for example, P of AA, and this is going to satisfy this problem. But superposition doesn't behave very nicely on satisfiable problems. So even this very simple problem has infinite saturation using superposition. And what this means in practice is that regardless of any of the parameters for superposition that you choose, the saturation is going to be infinite. However, both clauses are blocked, and both clauses can thus be removed. So it is an interesting question. Is there a procedure such that for a satisfiable problem I can actually reduce it to an empty set? Of course, not in general, but given some conditions. And we have created a procedure like this, which actually gets a finite Urban model and a problem, which is satisfiable because it has a finite Urban model, and using block clause elimination, using only block clause elimination and some additional technique very related to block clause elimination, it reduces the problem to an empty set. And this can be interesting from the perspective of, okay, I have a prover in which I have certain things such as block clause elimination and some other superposition related techniques, and how can I check if something is a model using only these techniques, and this procedure might be the answer. The second question was, can we use this can we use block loss elimination as in processing? And the answer to this is, unlike predicate elimination, no. And we came up with a counter example. This is this simple propositional 6-clause set, which is unsatisfiable. And the parameters of superposition are set so that you can perform superpositions or resolutions only between the grayed parts. Now, you can trust me that there are only those two clauses that are a result of such resolutions, and the first one is clearly tautology and it can be removed, but the second one is blocked on literal A, and if it would be removed, superposition wouldn't have a way to derive an empty clause, even though original set was unsatisfiable. And this shows that if we eliminate block clauses during saturation, superposition would lose reputational completeness. Now, we have implemented all of those techniques in a modern theorem prover, which is used for these kind of experimentations, called Superposition, and we have used the whole TP-TP set as our benchmark set, and we set the CPU time limit to 180 seconds. So hidden literals gave a modest improvement of only 11 problems, and we evaluated a lot of properties of hidden literals in our paper, and we actually found out what was already assumed, and this is that it is usually preferable to use short length of transitive chains. For predicate elimination, we see that using gates or definitions in first-order logic improves a little bit on predicate elimination, but that in general predicate elimination is a very useful technique to have. And we also saw that when combined with block clause elimination, predicate elimination is very effective. In conclusion, we have generalized some SAT techniques, implemented them in a modern solver, and evaluated them in a lot of different configurations. Our future steps are to improve the support for equality. It is still not perfect in, for example, hidden literals and block clause elimination, and we want to find a fragment of block clause elimination which can be used with superposition. And what they also do in SAT is they not only have SAT elimination techniques but also some SAT addition techniques, and we want to look into how can we use this together with superposition. Thank you.